Yeah, I have unmuted now. Okay.
Thank you, sir.
A very good afternoon, you all, again. Thank you, Bablu, just for initiating this whole concept of this Indo-Japan webinar series and inviting me to deliver a talk. Thank you. I also take this opportunity to thank other speakers who are delivering the talks in this particular webinar series. So today we are dealing with the liquefaction topic in general, and Professor Tobita has given the overview of the LEAP International Project and what are the activities happening in the framework of liquefaction analysis and thorough insight into the liquefaction mechanism through highly sophisticated model studies, particularly 1G model studies and centrifuge model studies, the scaling laws, evolution. It's very interesting to learn about the thing. So now I'm moving on to the another end of this liquefaction concept, that is the mitigation. As if we know that ground is going to liquefy, so how we have to take care of the particular ground, how to engineer that particular ground for the liquefaction mitigation. That's what the topic I'll be addressing today. So this is about the content what I have planned, which will be briefly talking about the seismic hazards with a special focus on liquefaction. And I will take you to a tour of some of the pictures showing the some liquefaction damages. And then I'll briefly discuss about liquefaction evaluation and what is the possible mitigation options. And then particularly I will take little bit more on the granular inclusions and stone columns. What are the liquefaction mitigation mechanisms they are working? And then finally concluding remarks is how I oriented. So mainly this particular talk is planned based on this particular publication, which is Engineering of Ground for Liquefaction Mitigation. So which is which was published in a book, Springer book, Advances in Indian Earthquake Engineering and Seismology. Uh, participants may refer to this one for more details beyond the topic and getting some important references and so on. So coming to the first thing, the seismic hazards and hazards related to earthquakes and associated effects. I will not go much into details as we all know. So there will be several variety of disturbances will be there. So basically due to loss of the strength, that is the less strength or less stiffness properties of various materials. We can talk about the soil, losing of the soil stiffness or material stiffness in the structure. There may be something, okay, sort of different loss of strength and associated damages. Particularly, if you see the what is associated hazards, you can say the ground shaking and amplification may be there, and then you may be having the structural hazards will be there, and then lateral spreading and associated failures, and then another major set of the seismic hazard is the liquefaction, which is our today's topic interest. So basically, just to define what is liquefaction, it's a reduction of the strength and stiffness of soil deposit due to generation of the pore water pressure because of undrained loading conditions. These are the, okay. So just to have this seriously, this particular topic has been taken into attention since 1964 after Japan and Alaska earthquakes. In principle, mostly this will occur in the saturated fine-grained soils, but also it was observed that some other soils also it will occur. Basically, when you talk about the liquefaction, we can just see the two varieties of the thing. One is the flow liquefaction, other one is the cyclic mobility. So with this brief introduction of the liquefaction, let us see some pictures of liquefaction damages, how they will appear. Starting from 1925, you can see that Sheffield Dam failed due to the liquefaction. You can see the extent of the damage and associated failure. So this is in 1988 earthquake, large railway line got damaged. So huge transportation infrastructure failure. and the associated building damages. This is 1999 earthquake in Turkey. So building was collapsed due to liquefaction. Some 2001 Bhuj earthquake examples, particularly in India. I must say, this is the 2001 Bhuj earthquake is one big earthquake which triggered, taken the earthquake related studies to much higher level. Almost many of the institutes have focused studying on this liquefaction or seismic earthquake related effects. 2010 New Zealand earthquake. You can see the witness of several of liquefaction signatures, those ground failures and all. Again, from the similar earthquake, you can see the extent of damage. So 2011 Christchurch earthquake in New Zealand, again magnitude 6.3. You can see the type of damages, soil coming out, and soil huge failures of the thing. So this is one interesting image which will explain the before earthquake and after earthquake and how various structures are suffering. I like this picture very much, which is schematically explaining various features of the liquefaction. So you can see some of these concepts here, like vehicle is going inside and underground structures are coming up here. All those things can be really seen here. Vehicle is going inside and some of the underground structure coming up. So this is a Japan 2011 earthquake. Some example here. So you can see the underground structures are coming up. Sendai 2011 earthquake. There was a sand boils. Nepal earthquake 2015, etc. etc. One interesting thing is that re-liquefaction. A site which has been liquefied earlier may also get liquefied depending on the seismic history, what is the new earthquake motion, how much strong it is. But there are some evidences that re-liquefaction can also happen. It's not that once it happened, it may not happen like that one. So the associated damage with the structures, this is one retaining structure, so which is totally collapsed due to the liquefaction. And pile supported structures and foundations may fail due to the liquefaction in different ways. One is the buckling failure or lacking the connection between the piles and the supporting cap, etc. And this is some of the already observed things. So what will happen if the liquefaction occur when you have the combination of the ground, improved ground and unimproved ground. You can see clearly the improved ground significantly behaved well in the liquefaction, reducing the damages. This is one particular example where you can see. This is again 2011 earthquake in a particular construction site where some part of the site was improved, so that area not liquefaction, where some other part was not improved, that area was liquefied. So it clearly shows ground improvement significantly. With these simple pictures, we can again relook into the definition. Loss of shear strength due to excess pore water pressure generation. And of course, cyclic mobility is a class where the gradual increase of cyclic strains. Here, it's not the complete loss of strength will be there, but there is a reduction in the strength, but more strains will be happening. Some of the signatures can be seen in terms of sand boils, lateral spreads, profile use, loss of bearing strength, and ground oscillations, etc. etc. So, which soils will get liquefied and how to predict? Here are the some of the conditions, so which were reported in various literature. So basically, whether particular soil site is liquefiable or not, we can just have a preliminary estimate. If the groundwater level is less than 10 meters and saturated soil layer at a depth of less than 20 meters, if it is there, then definitely there is a possibility of liquefaction. Then we can go for further analysis. And fines content, generally it is preferred to have less than 35% or plastic index less than 15. Even if the fine content is more than 35%. Again, D50 should be less than 10 mm and D10 is less than 1 mm. These are the probable typical soil properties. And besides this one, liquefaction of non-plastic seals has also been observed in the laboratory and in the field. Some references are there. And coarse silts and bulky particle shapes also are liquefied as reported from the earlier studies. And cohesive salts, earlier it was assumed that cohesive salts may not get liquefied, but there were several cases where the cohesive salts were also found to get liquefied, where they clearly defined what is the liquefaction and cyclic softening. Again, cyclic softening is another subcategory of the liquefaction. This behavior, cyclic softening in clays and plastic seals, you can easily find. So criteria for the fine grained soils, when you have fine grained soils, how to get into liquid in terms of the percentage finer and the liquid limit, natural water content and liquid index are the sum of the limits which are proposed by Chinese criteria and US Army Corps of Engineers. Beyond these sands and corrosive materials, gravels also tend to liquefy. There were some studies, some observations were found in the literature. So we cannot eliminate any of the particular category, but all soils tend to liquefy, but after meeting some of the particular criteria parameters. So these are some of various factors governing the liquefaction in the field. Not going into details, so just for academic point interest, I just mentioned these things to have some of understanding. So having that basic understanding about the particular soil site is going to liquefy or not, one can go into much more detail of evaluation of liquefaction potential. So various methods are available, starting from the simplified method, which is a cyclic stress-based method, and the cyclic strain-based method. And they are linked with the semi-empirical methods based on in situ test results like SPT, standard content test, cone penetration test, DMT, dialtometer test, or VS shear wave velocity measurements. All these in situ parameters can be taken into consideration, and using the semi-empirical method and using the stress-based and strain-based cyclic strain-based method, one can evaluate the liquefaction potential of the particular site. Besides this simplified method, one can go for the effective stress time history models also to analyze the liquefaction, and some studies are available using the probabilistic approach. And beside this one, so elaborated, very sophisticated experimental methods also one can go. Laboratory test methods can be in elemental scale, just to do some laboratory scale elements tests. In the case of cyclic tactile test, cyclic direct impulse shear test, cyclic torsion shear test, etc. And as a model test, one can think of like the shaking table test and dynamic centrifuge test, where in the previous speaker has touched this one, and shaking table and dynamic centrifuge test also. So I'm just touching here the simplified cyclic stress-based approach. So which what basically it tries to compare the load due to earthquake, how much load is coming out of the structure on the ground, and what the resistance the soil has to counter the loads, seismic loads what are being developed. So currently Ittis and Borlanger based methods are in practice. Of course, it was originally being developed by Seed and Ittis method in 1970s. So in this particular method, the load will be characterized in terms of the tau cyclic, basically is a function of earthquake acceleration and vertical stress, whereas resistance will be characterized, that is the liquefaction resistance of the soil. So which is a function of your in situ parameter. It can be of SPT value, or it can be of CPT resistance, and then earthquake magnitude, percentage fines, these are the things will come. So if you have the load and resistance calculated, one can calculate the liquefaction resistance in terms of a factor of safety as a ratio of resistance versus load. That's what a simple framework of this simplified cyclic stress-based approach. So this is one particular example I just presented here. Suppose if you have the soil profile here, and if you have the SP10 values of this particular site, so one can do some sort of calculations referring to the Ittis and Boulanger method, and one can calculate what is the factor of safety and evolve this particular graph here, factor of safety for with depth. And you can see where the factor of safety is less than 1, we consider that is a liquefiable soil. So please note that it's not that factor of safety is greater than 1 is completely safe. So excess pore water pressures can develop even if the computed factor of safety is greater than 1. So here one particular figure which I like it more bigger. So the residual excess pore water pressures, if it is 0 to 1 are there, and factor of safety against liquefaction, it is 1 to 2.5. That means even if your factor of safety is somewhere around 1.5 also, there is significant amount of pore water pressures up to about 35%, 0.3 times pore water pressures are there. The associated change in the effective stress, associated change in the strength of the soil need to be considered for evaluating the strength of the particular ground under these conditions. Suppose if you see the factor of safety within this region, within 1.25, if you say, the pore water pressures may go up to about 0.5, 0.5 to 0.2, it may go. So accordingly, we have to take a decision to what factor of safety we need to take. Accordingly, we need to analyze the particular structure. So besides this factor of safety approach, because the factor of safety is varying at different elevations, so what value to be taken, how to consider the particular site is a bit confusing. So liquefaction potential index LPI is another parameter, so which can be taken to evaluate for a particular site. What it will does means it will take the factor of safety values for a whole depth of up to 20 meters, and it will integrate the factor of safety values, and it will give you an index. Based on the index values, one can classify the particular site is going to what level of severity. Whether IL is equal to 0, very low, and IL is greater than 15 means its liquefaction is very high. So one can refer these particular references just to have the particular severity values. This is one particular example where Lee 2006 they presented in terms of factor of safety values and cumulative liquefaction LPI index value. So as I mentioned, there are some studies for liquefaction evaluation on probability based approach. This is one particular example where you can get the LPA versus liquefaction probability of ground failure can be taken. Again, based on the probability values, one can take the risk of liquefaction based on this particular values. So that's about the liquefaction potential evaluation. So some of the participants like students, postgraduate and undergraduate students, if they want to play with this liquefaction analysis calculations and all, they can download this software from this liquefaction software. Okay, and there will be a complementary evaluation version. One can use this software to have some understanding about the liquefaction evaluation. Yes, suppose after the evaluation, if you found the ground is liquefiable, so what to do? So basically, it's basically the improve the engineering properties and reinforce the soil to resist the seismic loads, and provide additional drainage, because we are talking that the liquefaction is due to the generation of excess pore water pressure, right? So if you provide the additional drainage so that generated pore water pressures are immediately dissipate, then you can also minimize the damage. And then again, we are talking this due to the groundwater level, and work can reduce the groundwater level in the particular site to avoid the liquefaction in the first. So these are the things one can in principle need to apply. So how to apply? That means we need to apply in principle, we have to apply ground improvement methods. That is what engineering of ground. Various ground engineering methods, ground improvement methods will be looked into, and accordingly it need to be applied. Right. So this is one flow chart which is provided by in 2001 report, a strategy to be considered for liquefaction remediation. So it has two parts. You can see here liquefaction remediation. One is the soil improvement, that's the engineering of the ground, which we will be dealing in this particular sector. And the other part is improving the structural design, how to make the structure more safe and all. Of course, these are another part. So our focus is on the soil improvement, that is nothing but engineering of the ground on this one. So we'll be taking here. So what are the ground engineering options? Various ground improvement methods. So if you recall some of the basic methods which can be classified in the form of the concepts, which is like densification. Densification, that means improving the density of the ground, making more stiffer. Ground is becoming more stiffer, densified, compacted and all. And another concept is the solidification. As you know, soil particles are very particulate in nature. Okay, if you solidify, if you make it as a coherent, very cohesive material, again it can resist the more shear resistances. Okay, that's one thing. And in some places we can replace with the suitable soils. If the soil is very weak and highly problematic, then we need to go for the replacement. And in some cases we will put some other elements in terms of the stone columns and deep mixing. Otherwise some reinforcement elements will be there. Okay, and then already mentioned the drainage and lowering the groundwater is another mechanism. So to provide the drainage is one thing, and lowering the groundwater level is another thing. So these are the concepts which will be applied for engineering the ground for liquefaction mitigation. So what are the associated methods in each particular category? Like sand compaction or granular piles or stone columns are the one thing, and vibratory probes will be used to densify the soil. Vibro compaction, they are all both of put together similar category. And a dynamic compaction, that means heavy tamping of the ground by dropping the heavy mass. And compaction grouting, displacement files, these are the one large group which can lead to densification of the ground and improving the ground strength and density and associated engineering properties of the soil. And in part of the solidification, mixing the soil with some additive materials. One is the deep mixing, mix with some other materials like lime or cement, whatever it is. Deep mixing and injecting the material so that it will interact with the soil and solidify. And quicklime piles is another class, and pre-mixing, mix the soils and then deposit there. These are the things as part of the solidification. Of course, replacement is a simple method where you can replace the suitable soils. And a reinforcement, of course, some of these above methods can also be as a part of the reinforcement. For example, stone columns and deep mixing also, it will form the columns which will be having the very high strength. That means they are reinforcing the particular ground. Providing the drainage, if some of these things, sand compaction piles and granular piles or stone columns, you see, being they are being the porous material, porous thing, they will act like a drains, and a drainage, additional drainage will be provided in the ground. Of course, to lower the groundwater level, one will apply the deep wells and trenches. These are overall class of the ground engineering methods, various things. So this is another interesting things, which method can be applied, what type of the soil, because of course wide variety of the methods are there. So depending on the type of the soil, one can see which is more suitable also. So this particular figure, which was presented by Mitchell in 2008, a general applicability of the ground improvement methods for most liquefiable soils. So this is the range, two range you see here, two borders. These are the soil grain size distribution curve range. This range, the shaded range, is the soils which are most liquefiable soils. So almost all ground improvement methods can be considered for the liquefaction mitigation. This is another strategic plan like what we were talking here. So what is the measures to prevent the liquefaction, occurrence of liquefaction? So whatever the principle and method of execution, this will give the overall picture of what is the principle and method and this one. So in principle, various methods applying different principles for improving the ground can lead to the mitigation of the liquefaction on a particular site. So with that overall view of the ground improvement methods or ground engineering options, as you see, the granular inclusions in the form of either granular piles or sand compaction piles or stone columns, so they can give various mechanisms. That means they will function as a reinforcement also. They will function as a drainage medium. They will function as a densification material method also. So because it is offering three different principles, so they are more effective in mitigating the liquefaction. So advantages, some of the advantages are low energy utilization and cost effectiveness while building the stone columns, increase the bearing capacity and reduce the settlements, and because they are providing the additional drainage, even otherwise the other than the liquefaction, they accelerate the consolidation and also permit the construction on fields. Even in the fields, if you are installing this one, vehicular movement, all other things can be done. Of course, besides this, all these general advantages associated with the granular stone columns, they improve the liquefaction resistance with the function based on all these behavioral improvements, and also prevents the earthquake induced lateral spreading because they are the high stiffness elements are there as a reinforcing effect, and they are able to resist a lot of shear forces. So earthquake induced lateral spreading can be prevented using this granular inclusions. So what are these stone columns? They will be installed in a pattern onto the entire ground. So as a columnar inclusions, you can see here, they installed for a height of h, and they are can be installed at a lateral spacing at a spacing s, and of the stone column diameter d can be considered. So like this, these are the stones. These are dots are the stone columns, which are arranged in a particular pattern. Entire ground will be covered. So based on these particular pattern and based on the spacing, one can calculate the what is the effective zone. Okay, each particular stone column will be controlling behavior will be controlled. That's particular. If you take this particular unit part, so we will consider this as a unit cell. Okay, so this is a drain, and unit cell is considered here. So a unit cell can be taken in this particular way. So this is the granular pile and the surrounding soil. Over this, you generally there will be granular blanket will be provided to distribute the loads uniformly and to maintain the strain compatibility between the neighboring soil and the stone columns, so that the whole composite ground performance is improved significantly. So as I mentioned, different patterns can be followed. One is the triangular pattern, square pattern, or hexagonal pattern. Accordingly, the unit cell contributing areas will be slightly different. So accordingly, the contributing areas will be calculated as per this one. So while analyzing this particular stone column reinforced ground, area displacement ratio AS for the stone column, which is the ratio of AS by A, is important parameter which will be considered for further analysis and understanding. So stone columns can be constructed using the vibro technique, vibro compaction, vibro replacement. Again, you have the wet method and dry method, and I'm not going into details. This is the rammed stone columns or case borehole method, which is a Indian method of stone column construction, so which is being practiced in different locations. So these stone columns generally being applied to different projects in railway embankments, highway embankment, infrastructure walls, airport runways, including all projects. Name any project, we can use this particular project for improving the ground and provide the benefit. So that's about the overall view of the what are the granular piles, what are the stone columns. Coming to the design aspects of this particular stone columns. So basically, design parameters involve diameter of the granular pile and the spacing between the granular pile and pattern of the installation. What pattern of installation need to be followed? The pattern of installation will be there, and information about the length of the pile, up to what length the stone column need to be installed. That means termination depth and gradation details of the granular material. The stone columns will be prepared with some material. So what is the material gradation details also will be provided. These are the design parameters need to be given. Of course, various useful references are available to work out these things. Very classic one is the FSWA report in 1983. And this is a PRIBE 2 documents are widely being used in 1998 and 1998. One is the basic design for web replacement, and the second 1998 is for the particularly prevent earthquake induced liquefaction. Okay. So they are widely being used. Tribe being the Keller ground engineering company people, they have widely being used. And another reference, this JGS, Japanese Geological Society 1998, they have compiled a lot of information across the Japan, various ground improvement case studies, failures and all. They have given some guidelines and important observations. Uh, One can use that one also for some reference of the thing. Coming to the Indian context, IS code 15284 is a part one, which is giving some of the guidelines, which is basically from MHWA and other Indian developments are being considered, which can be used for the designing of the stone columns. So as I mentioned, design parameters, what are the backfill material, generally crushed rock size of 5 to 75 mm, and what is the friction angle of the that material. It ranges from 35 degrees to 45 degrees, and patterns triangular or rectangular pattern typically with the spacing of 1.5 to 3.5 meters center to center, depending on the size of the project and all. Generally, diameter of the stone column will be in the range of 0.6 to 1 meter. This is again based on the size of the equipment available and the method of installation, etc., etc. So, area replacement ratio, another parameter which can be considered as 0.15 to 0.25 generally being used, area replacement ratio. And depth of the improvement, it is typically ranging from 5 to 15 meters. Of course, length of the stone columns up to 20 meters also, depending on the stratum. Up to what depth, what requirement, what is the functionality of the stone column, that we can decide. Area of the improvement, again, up to what extent of the area need to be improved. Suppose you have the project and built up area of that much. Okay, beyond that build up area, how much area need to be improved? Again, what is the application we are looking? Again, in the case to case, it will be varying this one. These are the various parameters need to be looked into and then design the particular thing. Approximately, the design loads for these stone columns would be about 20 to 50 tons approximately. So this is some of the information available for the material, how the material should be installed. Grain size distribution, okay, the gravel metal size distribution provided here. And the suitability number is another parameter which is available in the code for a particular material, whether it's suitable or not, that can be taken. Depending on the suitable material, whether it is a very good material or reasonable material, accordingly one can decide. So these two criteria. So one is observing this distribution and then calculating this suitability number. So one can pick the material here. So as I mentioned, basic relationship is area replacement ratio will be used. That is the area, AC is the area of the unit cell and the area of the stone column. Of course, different people use different terminology. And this N is another factor, is a stress concentration factor. What is this N? So because of strain compatibility, both the stone column material and the neighboring soil material will be going to same level of settlements. So obviously this stone column material being very stiffer material, it can take much higher stresses for the same level of strain compared to the stresses what the neighboring soil can take for the exactly same level of strain. So the stress concentrations will be different, stress values will be different. The sigma S is the stone column stress and sigma C is the neighboring clay stress. So the stress value ratio is that is any stress concentration parameter, another parameter which is generally being used in the design of the things. The same thing is explained here, stress concentration factor here. So generally it is stress concentration factor would be about 2.5 to 5 at the ground surface, and it will change around this one. And based on the strain compatibility, one can calculate the what is the stress in the stone column, what is the stress in the particular column material to have some understanding about it. So with the installation of the stone columns, we can improve the ground parameters. This is the improved SPT values. Okay, sand compaction piles or stone columns, if they are installed into the ground, the n values will be improved significantly. So the improved n values, a particular data was compiled here, and a trend line was fixed just to calculate what is the N1 treated value with reference to untreated value. Based on the area replacement ratio, one can have some estimate, some basic estimate. So this is another such results based on the SP10 value, initial values, and after the improvement, what are the SP10 values? There is some ratio. You can see the ratio from up to 2 to 12 times. It has been improved for this one. So midway between the columns, it's not uniform. Midway between the columns, we have some value, and center of the columns you have some value accordingly intensity. So that is another general understanding about the stone columns and their design philosophy and other things. Now coming on to the mechanisms which will be working for this granular column as per the liquefaction hazard mitigation. So already we have discussed what mechanisms are required to improve the properties, that reinforcement, drainage, densification and dilation, storage, etc., etc. So let us see here reinforcement effect, which was explained by Purushas et al. In 2006. So you have the stone column reinforced ground. You already saw this one in a plan, how it will look. In a cross section, how they will look. You can see the shaded elements are the stone column elements. They are highly stiffer elements. Okay. So when you are having some structure here and some earthquake is happening there, so you see in the earlier case stress concentration factor, what we saw is vertical stress coming onto the ground will be distributed for this clay and the stone column and maintaining the strain compatibility, right? Similar mechanism will come in consideration of the lateral stresses, shear stresses. So total shear stress, whatever is being generated by earthquake, will be distributed into tau C and tau S here, and accordingly it will be calculated. So you can say here large shear stresses will be taken care by the stone columns, which is the significant reinforcement effect. So with this reinforcement effect, the shear stresses which are coming onto the neighboring ground will be much lesser compared to the otherwise there is no improvement, no reinforcement of the stone column is available. And besides this, there is a drainage mechanism will be there. If you have the drainage, the water will be coming here into the drains and water will easily come onto the surface. So excess pore water pressures, what are being generated, they will be dissipated. So this particular drainage method has been investigated thoroughly from various models. This is one shaking table test where they have installed the sand piles and they have studied the pore water pressures. You can see here. So with the non-improved ground, you have the pore water pressure distribution like this one, and for the improved ground with different spacing between the piles like 3D, 3.5D, 4D, you have the pore water pressures. In all the cases, significant reduction in the pore water pressure, but you can also observe here as you reduce the spacing, so your pore water pressures are much reducing. That's what the observation. So this particular observation drainage effect was taken into the model as part of the analytical model originally by Seed and Booker in 1997. This is basically a consolidation model, radial consolidation model has been taken, and they have given the solution. Only difference is in the normal consolidation, we will be having only du by dt only. Because of this earthquake effect, there is additional pore water pressures being generated that will be considered into the model, and this whole particular equation will be solved using any particular numerical method. This is one finite difference model grid is shown here, and using the appropriate boundary conditions, one can solve and obtain the what is the pore water pressures at different things. That pore water generation model, this is a model what is being widely being used by D'Alba et al. 1976 model. This is being used for evaluating the pore water pressures that are being generated. So if you use this particular model, one can calculate what is the maximum pore water pressure ratio in a particular ground with the time, how much it is increasing for different area ratios one can see here. Of course, for a different given set of parameters. So this is the maximum pore water pressure ratio, and with the A by B is the area replacement ratio. In a different way it was presented, and what will be the maximum pore water pressure for a different given set of other parameters. TAD is another parameter which will be calculating the thing. Okay, as you can see for any particular condition, so if you increase the area ratio, okay, your pore water pressures are coming down. That's what the basic observation one can see here. So this was the originally developed Steeden-Brooker model, and then over the years, several researchers have worked on this one to improve and to provide more insights and to more parameters into the thing, and they have developed different models here. Particularly during my master's degree with Professor Madhav and my students, a couple of students worked and all. So we also did on some work in this particular Steeden-Brooker model. So one primary thing is densification effect is one other thing what one need to consider here. So as you install the granular column, okay, so the soil will get densified. The densification will be more very close to the stone column. It will keep reducing as you go at the end of the unit cell. That means the soil parameters within this region will not be constant. They will be changing with the distance from the center of the pipe. Okay, so the stiffness will be more here and stiffness will be less. If you talk in terms of the permeability, permeability will be less here, permeability will be more here. Accordingly, these considerations will be taken into consideration, and one can calculate the what is the equivalent deformation properties by considering two variations. One is the linear variation and exponential variation. That means modulus here will be more, modulus here will be less, and it is changing here. So this densification model is incorporated into this pore water pressure model, what is original Steeden-Brooker model, and some sort of analysis was given here. So further beyond this densification, dilation effect is another important parameter. The stone columns being highly dense in nature, so while vibration during the cyclic loading, there will be some negative pore water pressures being generated there. Okay, so what will do this negative pore water pressure? In addition to their natural drainage, they will attract more pore water pressures inside, and they will reduce the excess pore water pressures what are being generated in this particular soil. Thereby, it will reduce the total pore water pressure. That's what the concept. The concept has been included in the analysis, and it was shown the dilation effect is significantly reducing the maximum pore water pressure value here. So what we tried is to combine this densification and dilation effects into the model and showed its effectiveness together in reducing the maximum pore water pressures, which can be seen from this particular figures. Of course, in some researchers who worked on the soil fabric effect, so which is nothing but as you improve the ground, the pore water pressure generation will be changing. The associated effects can be taken into considerations, which will also further reduce the pore water pressures and all. So thus all the different mechanisms can be considered for improving the liquefaction mitigation using the stone columns. These are some of the examples, so which are using as stone columns for the liquefaction mitigation. Okay, so that's about stone columns. Besides that stone column methods, one can see various other type of the things like vibro compaction is another method. Of course, stone columns we have talked, and dynamic compaction and compaction grouting are the other engineering method options for improving the ground. So deep replacement is another use sector of ground improvement. So which can be generally two methods. One is by excavating, other one is by displacing the original soil. If you see various methods here, so these A and R are the excavating, and that means replacing mode of replacement by excavating the material and then putting the new material. Whereas in the other case, by displacement only will be doing. So next one is the deep mixing method is another set of the method. So what it will do, like shallow depth mixing what we do, and the shallow stabilization, we do the mixing of different materials. So the similar mechanism will work, but doing in a much greater depth. So what we need to have the very sophisticated equipment here. So like this augers and putting some material and mixing the thing, and finally forming the DMM columns, deep mixing method columns. The material, deep mixing material can be anything like lime mixed or lime cement combination or lime plus fly ash. These are different combinations can be used. But finally, what we do is we'll form a highly stiffened columnar material as a DMM columns, which will resist the lot of shear stresses and thereby reducing the liquefaction potential. So typical steps to be followed in design of this DMM methods can be seen by in this document, and some of the liquefaction related details using DMM are presented in this document 1996, which I'm not going into the details. The DMM columns can be installed in a different pattern. So like in the stone columns, whatever we have shown. So we can have the square pattern, triangular pattern, and a columnar pattern. Suppose you already constructed a building in somewhere, and if you want to put the whole ground as a isolate and stiffen the whole area, we can go for this type of patterns. Like different patterns can be chosen as per the requirement. So another useful and quickly improving the ground method is the deep dynamic compaction. Okay, like many of the construction sites will be having the heavy equipment like the crane, high lifting crane, or some sort of excavator and all will be there. If you have a huge tamper dropping weight, and if you are dropping from a larger height, then you can compact the particular ground. Of course, there is some requirement, suitability of the particular ground need to be seen. Loose and partially saturated fields and saturated free drain soil should be there. Okay, but it will not work for the not for the clay soil having which is having the plasticity index greater than 8. It will not work, but otherwise some other ground we can work. So typical weight of this tamper will be about 5 to 40 tons depending on the depth of the treatment what we are looking for. And again the typical drop from a height of 10 to 40 meters, again it will be depending on the what level of improvement. So this dynamic compaction design aspects can be seen from the FHWA report, whatever is shown here. That's what in general the improving the soil. Basically what it will do, it will create a character type, and one can calculate the how much is the deformation, how much is the improvement in the density. And obviously if you are improving the density, the associated parameters, strength parameters, whatever you take C or phi or shear velocity, whatever it is, obviously you will get some lot of improvement. Obviously, when you have this improved strength parameters, you will have the lot of resistance and your liquefaction can be mitigated. Some of the liquefaction mitigation related issues have been addressed by several researchers depending on several projects. So that's about broadly we can say granular piles or stone columns or sand compaction piles or the columnar inclusions which we can see for the improving the ground improvement. And we have the deep mixing columns, and we have the deep replacement methods, and another method is deep dynamic compaction. These are the various class of the things which can be used for improving the liquefaction mitigation of a particular ground. So this particular thing you will show the comparative assessment of engineering of ground methods in terms of the improved SPTN values. As earlier I have shown the one expression to which we can calculate the SPTN values improvement. Here sand drains and compaction, what's the range of the improved values are given in this particular slide. So we can see there is a significant improvement can be obtained in the sand compaction and sand drains or compaction methods compared to unimproved values. Besides, in terms of the ground subsidence during any liquefaction or earthquake related thing. So this is after 1995 Hyogoken Nambu earthquake for the Japan. Again they have obtained the data from various sites Okay, so you see here there is unimproved SPT, and what is the unimproved gas, what the subsidence is shown here. And in the case of preloading, what is the range of the deformations they have seen? In the case of sand grains plus preloading and rod compaction and sand compaction piles, under this case, what is the level of ground subsidence you can see? You can see if there is no improvement, it is about 100 centimeters of close to 1 meter of settlements were there. Whereas if you apply this improvement methods, you can see about 30 centimeters to almost 5 centimeters deformation was observed for different projects. That shows the effectiveness of the these methods. So with that, I'll come to the concluding remarks. Uh, as you can see, some of the pictures what we have seen, liquefaction is the most hazardous damage during an earthquake, because liquefaction, the associated structural damages are particularly in the case of huge public infrastructure, highways, railways, overbridges and all, lot of damages will be there. Okay, so in principle, one can apply ground improvement methods, that is engineering of ground, are extensively employed for liquefaction mitigation. So basically, the main principles which we will be looking for this ground improvement method is the densification, solidification, reinforcement, and drainage. Among various methods which are listed, and few of them which were we discussed, stone columns, oblique granular piles are the method are widely adopted. Because why? Because they cover the three main principles. That means densification it will cover, and reinforcement it will cover, and it will also provide the drainage facility. Because of these three principles and associated advantages, they are widely being used. So other methods also can be used depending on the application of things. Basically, some order of priority was given. I'm just putting a question mark here. That means it is not a standard order of priority. It may change depending on the site and of economics and availability of the methods, everything. The priority may change. Just for the case, sand compaction piles, deep soil mixing, and dynamic compaction methods may be considered in the order of priority. So, looking into the broad spectrum of the liquefaction phenomena and its mitigating strategy, various parameters are involved in both the things, even in liquefaction criteria and this mitigation strategy. So, selection of any particular method for any site depends on various engineering and particularly economical. Being an engineer, we have to make the particular project to be more economical, and also feasibility factors. That means against a particular site, what material available, what agency available, okay, what type of equipment available, that feasibility also looks into picture. So all these things need to be considered for selecting a particular method. This one. So it is advised that one should work on different possible options to suggest the more viable and economical ground improvement method for mitigating the liquefaction. With this, thank you for patient hearing.